And so we are going to learn the first 3 of the 5 techniques for determining whether a series converges in general or not. Yesterday, we learned a way to determine divergence right off the bat. And that's a great method, because if you have a series that diverges and you recognize it right off the bat, you want to point that out so you're done. There's no work to perform. The work is usually in determining if it converges or not. So I'm gonna illustrate a simple picture, but there's a couple of conditions on the first one. The first one actually has quite a few conditions. So let's consider I have the following, or actually I'll use n, sorry. N equal 1 to infinity an, where the following is true. I'm going to start with the statement that A1 is greater than or equal to A2 is greater than or equal to A3 forever. The terms are going to get smaller as I go. They can stay the same, but they're going to get smaller in general as I go. Okay, so first thing is, that would mean that my terms are getting smaller, they're bounded. And the second thing is, my terms are going to approach 0. So I'm going to pass the nth term test. But the key is, all of my terms are going to be positive and getting smaller. So if I drew a picture, just sort of a simple picture. Think of this going forever. And don't think of it like a regular XY plane graph. Just think of it as, I'm going to put down, this will be 1, 2, 3, 4, 5, and so on. All right, so A1, let's say, is here. And then let's say A2 is maybe here. And then A3 is here. And then A4 is here. And then A5, and then A6, and A7. So you get the idea. They're getting smaller as I go. I want to add up this infinite sum. Well, yeah, but actually, I'm not interested in the total. I'm interested in, does it converge or diverge? So let's consider the following. First of all, if I wanted the area, one way to do it, in this particular situation, one way to set up my area would be to make little rectangles, okay? To make rectangles of each of the heights here. So if I went up to, actually, I'll do that one. No, I'll keep the same color here.
I know this isn't the specific scenario that we're looking at right now, but couldn't that also apply to, say, an equals 300 minus n, where you have a linear descendant below the and then it wouldn't approach 0, it would just continue on into negative infinity,
and then that one would diverge. So we're going to start with something that passes the nth test. By the way, the question, it's a great question. What if I have something, like you said, it's linear in nature, but it's going to go down to negative infinity? It failed the nth term test because my limit of the nth term wouldn't have been 0. So that's why we're not going to consider that one, because we're already done. So we're going to approach the x-axis. But remember, the harmonic series also had the same behavior. So that wasn't enough. Just simply approaching the x-axis isn't enough, but it's a starting point. So I want to make rectangles here, okay? I want to make rectangles of my heights, and I want to do it like this. Now, tell me, if I said the area of the rectangle would be this height, wouldn't it? Because it's 1 unit wide and it's this unit tall. So if I added up the area of the rectangles, that's one way of thinking about the sum. So the next thing I want to do is, I want you to think of a curve that's going to pass through these corners. Okay, and let's call our curve, for lack of a better name, let's call our curve y equal f of x. Where this would be f of 2, this would be f of 3, this would be f of 4, and so on. And you notice where I started my rectangle. I started it going this way. So the height of this rectangle is simply A2. The height of this rectangle is simply A3. The height of this rectangle, and so on. Now, what can you tell me if I asked you about the integral from 1 to infinity of f of x dx? Is that going to be greater than or less than the sum? What do you think? Is the area under the curve going to be greater than or less than the sum?
Less than?
Greater, because you have the
Right.
space above.
Yeah, because the curve's above. In other words, the sum would be just the areas of these guys added up, and my curve's above the rectangles. Does that make sense?
Oh, I see. You're
The
comparing
area
it to
under the curve clearly is going to be
rectangles.
greater than, okay? Doesn't matter, I'll write it on this side. So now, but you notice that I did not start my sum at 1. I started my sum. Ooh, mute yourself. Crazy echo there. You notice that this sum, the height of the first one would have been here. I started with the height here, so that technically is starting at 2. That will matter. Oh, so I literally subtracted the first term. So everybody stare at this picture. This is our first result. Okay. I'm gonna write it up high because I'm gonna need more space. So right now I've just shown that the sum starting at 2, I had deleted the first term, if you will, is less than the integral. Okay. Now I'm going to give you a slightly different picture this time. What if instead this time I said, let's go ahead and make our rectangle all the way up. Let's make that our rectangle. Then the second rectangle obviously would be this guy. And then the third one would be here, and the fourth one would be here. So now I'm actually starting my sum at 1. What can you tell me about my integral compared to the sum this time? Is my integral?
The sum would be greater.
The sum will be greater. So do you agree that at this time I can put the sum from 1 to infinity? Whoops. What we're trying to do is bound the sum by using the integral, figuring out, is there a boundary? Because I probably can calculate the integral, but I may not be able to calculate the sum. Okay, so here's something we do know. Let's look at that first summation. Isn't it true that this equals this minus the first term? This is the sum from 1 to infinity, and if I subtract the first term, then I have the sum from 2 to infinity. That was the lower set of rectangles. So if I rewrite that one right there as n equal 1 to infinity of an minus the first term, now I've got a new way of considering this. What I want an inequality where I have the sum in the middle. I don't want the integral in the middle. I want the sum in the middle. So here's what I know absolutely. I know absolutely that right now I know that's smaller than this. Okay, I know that. So I'm going to write that right here. I'm using a little bit of clever algebra here. But now look at this statement right here. Isn't the sum going to be smaller than the integral plus a1? Check that out. Now what I've got is I've bounded the sum. I don't know what the value of the sum is. That's not important. I want to determine the convergence of the sum. Now here's an absolute. A1 must be finite. The first term of my sum is finite, period. It's not 0, but it's probably not very big. I mean, it could be, but it's a finite number. I have just proven if all of my terms are positive and they're getting smaller and approaching 0, that was a major assumption. But if all my terms are positive and they're approaching 0, I've just proved that the sum is between the integral and the integral plus the first term. Since the first term is finite, this means simply if the integral converges, the sum converges. If the integral diverges, then the sum diverges. Are they going to achieve the exact same value? No, it's a strict inequality, but the value of the integral is going to be very close to the value of the sum. Again, I'm not interested in the value, I'm interested in whether it converges or not. Question?
Could you just say that again? Like what you just stated?
We're trying to figure out if this guy converges or diverges. Now, by the way, I've got posted notes where I've done all of this. I've got, just so you know, I have some really good hand illustrated pictures. I took great care in
Nice.
drawing these using graph paper to illustrate what we just did. I don't know if this converges or diverges, but with the situation that we assumed that my terms are getting smaller and approaching zero, I can guarantee that this is between the integral and the integral plus the first term. That's an absolute guarantee. Therefore, either all of these guys converge or all of these guys diverge. I can't have a finite number between infinities, and I can't have infinity between finite numbers. So
This
they're
feels like a
all
sandwich theorem.
kind of like that, but it's a simpler conclusion in that they have the same behavior. We say they all converge, but they all diverge. So you good with that so far? So here's the thing. If I have no other way of testing my series, I can always do an integration. Now, this is never going to be your first choice because it generally represents the most challenging way of doing something. It's neither good nor bad, it just is. So let's do an example. I think I made myself, hold on. I didn't write any of these down. All right, we're going to start with a simple example. Let's start with something we already know how to do pretty easily. Okay. I want to determine. I want you to do something like this. I would like to determine if this converges or if this diverges. Now, right now, we have no idea. Now, this is going to pass the nth term test. My terms are going to get smaller as n gets bigger, and obviously the limit as n grows without bound is going to be 0. That's not the concern. I'd like to know if this converges or diverges, so we're going to use the test we just did. We're going to use the integral test. Now, you can certainly integrate a function of n. That is not a problem. I have no problem with saying, all right, I want to do the following. I want to do this. Except people look at that and go, oh, that just scares me. I don't know what to do with n's. So this is why everybody changes it to this. Does it really matter what letter of the alphabet I'm putting there? No, it's just when we do an integration, we'd rather see x's. It just feels more comfortable. Now, what are my limits of integration though? They're going to mirror this. So it's going to be 1 to infinity. Okay, it has to mirror that guy exactly. Well, that means this is going to be the limit as t goes to infinity of 1 to t of 1 over 1 plus x squared dx. Do we know the antiderivative of that quantity?
Inverse tangent.
It's inverse tangent, so that's a friendly one. By the way, integral test in general is not, it's not always friendly, but occasionally we get lucky and we get a really simple function. So this is going to be inverse tan of x, nothing weird going on. And I'm going to have inverse tan of t minus inverse tan of 1. All right, let's start with inverse tan of 1. That's the easy one. What's the inverse tan of 1? Tangent of what angle is 1? You really should know that one. Now,
45 degrees, yeah.
so what's the
Or do you want in radians?
It's not a question of want. There can only be. Hint, hint. There's no such thing as a degree answer on any.
Quarter pi.
So
Okay.
what Adam's suggesting is the right thing to do. Figure it out in
5/4.
degrees. Always figure it out in degrees first, then translate it to radians. So it's pi over 4. Oh, this guy. As t grows without bound, inverse 10. Oh my God, how am I supposed to do that one? We did it yesterday. You guys remember? I drew you a picture yesterday. I'll draw the same picture.
It's pi over 2.
Yeah, we showed yesterday that as it grows without bound, that horizontal asymptote is pi over 2. Part of the reason I showed you that yesterday is because it does come in handy. Oh, so what is my answer? My answer is
Negative pi over 2. Or pi over 2, sorry.
pi
Pi over
over 2
4.
minus pi over 4.
Pi over 4.
Pi over 4, just pi over 4. Now, question, does that mean the sum is equal to pi over 4? No, it means the integral is equal to pi over 4. Oh, but pi over 4 is finite. Pi over 4 is finite. So therefore the sum is finite. I said, but what does the sum equal? I don't know. But at this point, I would just use a computer to actually say, all right, add up the first bazillion terms and tell me what you get. What I just showed you a moment ago suggests the following statement. What's the first term?
1/2.
The first term is 1/2. This is what we just showed a moment ago. In other words, we are bounded by the value of the integral and the value of the integral plus the first term. I don't know what the sum is, but it's somewhere between pi over 4 and pi over 4 plus 1/2, which means that the sum is finite. Again, the ability to calculate the sum is not our interest. That can actually be reasonably approximated, but that would require technology. We're not even interested in that. That means you just simply do a simple do loop on a computer. You say, well, how would I know the technology would be working? If I go 1,000,000 terms out, think of the size of your denominator. You're affecting like the 15th decimal place at that point. Yeah, this thing's going to converge pretty fast. And numerically wise, I don't have to go very far to get really reasonable numbers. So
do you want that as our final answer?
No.
Say,
I'm showing you what we just showed here. That's what we just showed. But the question was, does this converge or diverge? So your answer is going to be simply, this converges by the integral test. That's the conclusion. This converges by the integral test. And if you really wanted to get down and dirty, that's where it's going to converge somewhere in that interval, but I don't know what it converges to. I just know that that is an absolutely correct mathematical statement. I don't need that, but that's what we just showed. I just need the fact that my result of the integration was finite. Now let's use the integral test on the harmonic series, because we proved yesterday that the harmonic series diverged. But my proof was kind of a clever proof. Remember, I grouped things and then I grouped things and I grouped things and I went forever and ever and ever. And you could say, that's kind of weird. Now, are you guys getting something flashing on your screen? I'm getting a flashing symbol on my recording. It's making me worried.
I just see that.
Something flashing. My recording symbol is flashing. Have I been at any point freezing or breaking up to anybody?
I mean, all the time for me, but
No.
No. Okay.
It's been good on my end.
Okay, semester, I just want to mention, last semester, I'm in the middle of a lecture and all of a sudden I get this on my screen, battery low, and then it turned off. It's plugged in. It's a brand new Surface Pro that's plugged in 24/7. The battery can't be low because it's not using the battery at all. And it kicked me off Zoom. It took me about 15 minutes. I had to use the other computer to get back on. It was terrifying. I felt like I was out in the middle of the ocean without a lifeboat or something. And we eventually made it work, and I never figured out what happened. And when I replugged it in, it recharged itself immediately, but it's doing wonky stuff right now. So that makes me a little concerned. I don't want to get kicked off. All right, let's consider the harmonic series, but now let's use the integral test, because the integral test, I just derived it. It's absolute. If you have a series where the terms are getting smaller and approaching zero, absolutely, you can use the integral test. It doesn't mean you should, it means you can. There may be easier tests. Hint, hint, there's almost always easier tests. So let's consider this guy. We already know what this is going to do, but now we're going to do the integral test to prove it. So what I'm going to do is do the integration from 1 to infinity of 1 over x dx, which I believe we did two days ago with the infinite painters, if you remember. Yeah, this is the one that caused us to go into bankruptcy, if you remember, because it was too big. 1 to t of 1 over x dx. And that is equal to the limit as t goes to infinity of natural log absolute value of x from 1 to t, which is limit as t goes to infinity of ln t minus ln1. Well, natural log of 1 is 0, but as t grows without bound, natural log of t is infinite. So the value of my integral is infinity. And I just said a moment ago, if your integral is finite, the sum is finite. In fact, you can even tell me what two numbers it's bound by. If your integral is infinite, then your sum is infinite because, again, the integral and the sum have to have the same behavior because they can only differ by a very small constant. So because the integral produced infinity, we'd say this, again, diverges by the integral test. We're going to have multiple tests, so you always state your conclusion and indicate which test you use to come up with that conclusion, because the different tests have different structures, different formats, and different ways of making the conclusion in the end. Okay, so that's the first one. This is the first one because it's easiest to derive, but it's probably the one you're going to use the least. We're kind of going to go in reverse order here of use. All right, now the next one, someone used the term squeeze theorem or sandwich theorem earlier. This one is actually even more such. So I want to give you a simple thought process. All right. Let's say last year I made an infinite amount of money and Nicola made more than me. Can you make a conclusion? I made
Nicola's richer than you?
No.
You have drained the banks of the world.
No.
Conclusion, money has no value to you now.
All right, you guys are
Okay, can you repeat
really wise. I'm giving you the only way to interpret the next mathematical thing, which is the easiest test that exists, but people miss it most of the time because they're not paying a lot of attention to the detail. I made an infinite amount of money. Nicola made more. Can you make a conclusion about Nicola?
She made more than you.
I said that. That's not a
Oh,
conclusion.
sorry.
She
made an infinite amount of money.
She made more, therefore
She made infinite.
she made an infinite amount of money. So if something is infinite and something else is larger, then it must also be infinite. That's 50% of the conclusion.
Just since we were talking about it earlier, my name is pronounced Nicola.
Nicola, okay.
Yeah.
now you tell us, Nicola.
Yeah.
That's funny.
That's why I said she instead of saying your name, is because I didn't want to say your own.
It's because it's one of those because I know a few Nicoles, but I also know a Nicholas, so that doesn't really help, does it? Okay. Now, I made a finite amount of money last year, but it was positive. I made a positive finite amount of money last year. Okay, because that seems redundant. And let's say Tom made less than me, but it was still positive. I made a finite amount of money and Tom made less than me, but it was still a positive amount. In other words, he didn't lose $1 million. I made a finite amount, Tom made less, but positive. Can you make a conclusion?
I made a finite amount of money.
Finite amount of money. By the way, the reason I said it had to be positive, if I said I made a finite amount of money and I said Tom made less, technically, couldn't that be negative infinity? Because negative infinity. So that's why I said you're bounded by a positive amount. So I'm giving you the two scenarios.
Or zero. If he made zero, that would also be.
I'm giving you two scenarios. So I made a finite amount of money. I said Tom made a positive finite amount of money. Okay. Tom made a finite amount of money, clearly. Now, the first example I said, I made an infinite amount of money. Nicola made. Nicola, sorry. Nicola made more, you'd say infinite. Now, I'll give you a different scenario. Last year, I made a finite amount of money. Cain made more than me. Can you make a conclusion? I made a finite amount and Cain made more.
No, you can't.
So either finite or infinite, you don't know.
So therefore, no conclusion can be drawn. The way I like to say it is you're on the wrong side of the inequality. Last year, I made an infinite amount of money and Adam made less than me.
So you don't know.
Same problem. It could go either way. So this type of test is where you're bounding things. You have to be on the correct side. You have to be bigger than something that's already infinite or smaller than something that's finite, but still be positive. This is called the direct comparison test. It's by far the easiest one. It's the one we'd want to employ the most often because it not only requires the least amount of work, it's the easiest to conclude, but also we probably don't get to use it all that often. So
Does this account for oscillations, or is that just not a thing when it comes to this test?
Not yet. That will come up actually on Monday. Almost everything's fair game. Okay, so let's consider a scenario, and I'm going to do one we just did. Just a little while ago, remember we proved that 1 over n squared plus 1 converged. Agreed? We proved that. So I'd like to say, I'm going to use a simple case here. I've got something that looks like this. I'd like to know if this converges or diverges, but I don't really want to start from scratch, and I really don't want to do the integral test. Now, let's compare
To the inverse tangent.
no, let's compare to this sum here, which I'll put, which we already showed
It converges.
converges. I'm only using, this is not one you would use in general, just because we just did this problem. I'm going to be lazy and use that result. Well, how am I supposed to use that result? Because is it true? Is it true that 0 is less than 1 over 10 plus n squared, and that's less than 1 over 1 plus n squared? Is this true?
Yes.
Because I got a bigger denominator. It's never, in fact, this is true for all n when? Well, for every n. So now remember yesterday when I used the term for all n bigger than a capital N, I said at some point. Well, that's our some point. It's pretty obvious that because this has a bigger denominator, for every value I can put in for n, this is a true statement. And since my sum starts at 1, this is true from 1 on. You know, what if it wasn't true until 10 on or 1,000 on? Well, at some point, it's always true forever and ever and ever. Since term by term, every term here is smaller than every term here, then I can say the sum from n equal 1 to infinity of 1 over 10 plus n squared is less than the sum. And here's the key. I made a finite amount of money and you made less than a positive, and it was positive. My conclusion is you made a finite amount of money. I just showed that term by term, this was always smaller than this. Therefore, this sum is always smaller than this. We're done. Because that one converged. This here, I'll say it out. This converges by the direct comparison test. Now, we are lazy mathematicians and we get tired of writing things like direct comparison test over and over again. So do you know what we universally write about now?
TCT.
Yes.
So smart, Adam.
Well, I would
like
do go
GNE,
back
right?
to the all real numbers greater than 1. Where's that 1 coming in? Is that just the first term?
No, it's not all real numbers. It's all
All
n.
real n, sorry.
No, not reals. No, these n's can only be positive integers. It's these guys. Remember when the example I did yesterday, you're talking about your indices. Your indices can only be integer values. They can't be, 0.5 or pi or √2 or something like that. So 1, 2, 3, 4, there it's a counter, it's an index. So I want to say the first situation where it was true and then it's true forevermore, but it's 1, 2, 3, not interval 1 to infinity. That would be real numbers. This is counting numbers.
Okay.
Would it change anything? Well, no, but I'm not using real numbers. I'm only using counting numbers in my indices. This is direct comparison test. This is a nice one. So before we go any further, the most common thing you're going to compare stuff to is the next thing, and I want to show it.
Before you
Yes,
erase
sir.
it though, Professor, that notation of for all n greater than or equal to 1, is this part of the answer that we also need to be providing, or is that just for us to see right now?
No, you should always say that because You're saying, I'm claiming this is always true, or I'm claiming it's true from
Right.
some point?
Yeah, I was just making sure this is something that we're also including, not just for you to show us.
No, it's part of it, but I could have an expression that's a little more complicated. For example, if I had n's in numerator and denominator, I might have to do some algebra and say, okay, this is not true until n is at least, 10 or 20 or 30, but then I can see
Okay.
it's always true after that. It more often than not, by the way, it's going to be the first instance more often than not. So that's not really a major concern.
Professor,
Yes,
what's that symbol? What's that? The upside down A symbol is called
for all.
for all. Okay.
Yeah, I've actually used that probably 7 different lectures this semester, and I actually spent some time on last lecture. I want you guys to get used to it because it's a very common. In fact, if in your Calc 1, you should have used this actually quite often, epsilon delta proof. Oh yeah, you can use words, but math people love using symbols because, well, it's not just that we're lazy, but you're going to be developing more symbolic notation as you go. So what about the following? This is one, probably the most important one we're going to look at. I would like to know whether this converges or diverges. Well,
That
shouldn't
ends the P.
Yeah, don't you think it should matter what P is? I mean, wouldn't that, we just did the harmonic series, so we
Don't
know
worry.
it diverges when P is 1. Right? We know this diverges when P is 1, but if I do the integral test on this, I would be doing this. Does this ring a bell?
Yeah, that's
Tell
for
me this
the
rings a
rule
bell.
we created for P is less than 1.
This one we just did
We
divergence.
just did this one. You remember
Yeah.
I said, this result's going to be really important in about 2 days. I think we did this one 2 days ago. We know that this converges
Wait, what?
when? Do you remember? It converges when P is
Greater than 1.
strictly greater than 1, and it diverges when P is less than or equal to 1. We proved this in class. And now that you have the integral test, the behavior of the integral will be the same as the behavior of the series, meaning they converge or diverge for the exact same exponents. So this sum will converge as long as P is greater than 1. It will diverge when P is less than or equal to 1. We have a really clever name for this kind of series. Now remember, we're the people who brought you, if you have a point and a slope, the equation is the point slope formula, we're really clever. The rule for taking derivatives of products, of course, is called the product rule. Yeah, we name things after what they are. So the theory, the formula that does this is usually called the formula that does this formula. So a series where that exponent is P in that position every time, you'd never guess this one. We call this one, a P series. Forevermore, a sum of this form is called a P series, but I want you to make sure you pay attention. That P is in the denominator, not in the numerator. Okay, so if I put a large exponent on this, definitely it's going to converge. But if I put a small exponent, or worse, I move that n into the numerator, it's going to diverge. Okay, so when we're doing the direct comparison we just did, the most common direct comparison is usually directly onto a P series because it's the easiest one. So let's try another one. We'll do another direct comparison here. I love using direct comparison, but again, the inequality has to be just right for it to work. So let's consider the following. We want to talk about, let's say, I have the sum from n equal 1, and we're going to do, how about, if it's relatively simple, I want to do n minus 3/2, 10 on top of it. Can you think of anything we could compare that to that has this form?
Can you
Well, don't you
Wait.
just take the 10 out and then you have 1 over.
No, actually, I don't need to take the 10 out, but can you think of a series where you know its behavior? That would be a good thing to compare it to.
Isn't it inherently bigger than 1/n?
So therefore compare it to
1/n.
1/n. Yeah, so compare to, and always do what I'm doing here. Always indicate what you're actually comparing it to, and even more importantly, what is the behavior of the thing you're comparing it to. So we're going to compare to the sum 1/n a convergent or divergent.
It converges.
No, it diverges.
A divergent. By the way, you could say P series or harmonic series. It actually is both. Now, why do I want to compare it to that? Because isn't it true that 1/n is smaller than 10/n minus 3/2? You notice I made the denominator here smaller and I made the numerator bigger at the same time. So this guy here is way bigger than this guy. Does that make sense? The guy on the right is always bigger than the guy on the left by at least 10 times. So this is true. By the way, I don't need the 0 at the other end. I'm comparing it to something that's bigger than itself for all n, again, greater than or equal to 1. Because so if this statement is true, then we can say, if that statement is true, then we can say this statement is true. We start by comparing term by term and said, yep, it's always true. Therefore, when I add all these guys up, it's smaller than when I add all these guys up. This was infinite. This is bigger. This is my situation. I made an infinite amount of money and somebody else made more. Okay? Everybody got that? So therefore, what's my conclusion?
Therefore, the sum of
this diverges by the direct comparison test. Did I do any algebra whatsoever? Oh, it's been a statement, piece of cake. Not always going to get that lucky though. Why will I not always get that lucky? Let me do almost everything the same. Tell me if I can use a direct comparison. You know that the sum of 1/n squared is a convergent P series. You now know that based on what we just said. Okay. Can I use a direct comparison on this one?
you cannot,
Why not?
because 1/n squared minus 7 comes up with a smaller number than the other one,
Which one's bigger, left or right?
right?
Left.
No,
You're
right.
shrinking
Sorry,
the
yeah.
numerator.
Can't see
So-
anything, the screen's frozen.
Your screen's frozen?
Mine at least, I don't know.
You're a good professor. He's
Am I
always,
freezing on you? I'm getting worried because what I'm looking at myself, doing the what is it, the robot thing, I'm looking at myself being short bursts of freezing and not really continuous motion, and it concerns me, but we haven't been kicked off yet. I know the sum here is going to converge, but the sum here is going to be bigger than the convergent series. So that doesn't help me. Infinity is bigger than a convergent series, and finite can be bigger. I'm on the wrong side of the inequality. I cannot use the direct comparison in this case. What if? What if that were a plus sign? What if that was a plus sign?
then you'll be fine because all of a sudden
Because now it would be.
switches.
So that's what I mean about the direct comparison. You have to be on the correct side of the inequality. Direct comparison is extremely limited, but when it can be used, it is always the fastest, easiest, foolproof method. You just can't always use it. So now the next one I'm going to show you, the third one of today, is one of the most commonly used ones because it doesn't have a whole lot of restrictions. It's a little more work. And so now I'm going to introduce a new concept that we briefly touch on in Calc 1. And well, depending on who you have for Calc 1, you might not touch on it at all. And I've used the term before. It's called asymptotic convergence. Now, when people think asymptote, an asymptote is a line, right? So if I have a curve, that's disappearing into the x-axis, like, e to the negative x. Oh, I just got the message here. Okay.
Yeah, now I'm getting you super robot.
Okay, I just got the message that it said my battery's running low, so that's really bad. That happened before.
I'll leave the class after you're
Okay,
done.
hold on a
So
second.
don't worry about it.
It's no longer. Oh, now it's flashing in. So I think here's what we're going to have to do. I'm probably going to have to switch to the other computer. So what I'm going to do right now, nobody go away. I'm going to go ahead and stop the recording. Okay, and I will save this. I'll bring up, I have a second laptop, fortunately. It's not as good. I will do that one and then we will continue. And so when I post the lecture videos today, there'll probably be two, a part 1 and a part 2. Everybody cool with that?
You're no longer frozen on my screen, and you have,
Yeah.
That
Hey, I'm
recording
back.
thing is
Good.
flashing though, which means it's going to kick me off, I think, at any minute. I got
Sounds
the
good.
low battery symbol at my end. So when I got the low
Okay.
battery. So let me do this. I'm going to go ahead and log off. I'm going to log on to a different computer. Okay.
Sounds good.
All right. Give me like 5 minutes.
Are you sure it's plugged in?
Yeah, it really can't be unplugged where I'm standing.
Can you like maybe unplug it and replug it?
What I did before is I just jiggled the plugs, unplugged them, plugged them back in, unplugged them, plugged them back in, and then everything was fine.
Does it indicate that it's getting plugged? Because it indicates when it's like, hey, I'm charging, whatever.
Hold on. Well, the thing is, let me unplug it, plug it, and see what happens.
Yeah, I'm on tech support.
Yeah, I'm still getting the flashing thing. Last time this happened, I lost all power, but when I plugged it in and unplugged it, it recharged itself actually really, really fast. This did happen once. So I'm going to leave and then I'm going to come back on the other computer. It'll let me actually leave. There we go.